Hi everyone. Today we have another session in our DevConnect series where we'll be discussing the ODA Visualize SDK, a professional visualization engine for a wide range of data. To start, we'll provide an introduction to the project. We'll review its key capabilities, discuss the latest features and updates, and then share information on some of the topics we are currently working on. After the presentation, we'll hold a live Q&A session. Engineers from the Visualize SDK team are here with us today and are ready and happy to answer your questions. So we can see everyone here. As mentioned, let's begin with a brief overview of what the Visualize SDK is. The Visualize SDK is a general-purpose rendering engine designed to visualize different kinds of data. For example, it can handle 2D data such as plans or maps. It's important to know that Visualize SDK comes with ready-to-use standard features for 2D models, including layers, line types, text styles, line weights, and more. The Visualize SDK is also well suited for various 3D data, often used in fields like engineering or architecture. When working with 3D data, materials play a key role in visual representation, and the Visualize SDK offers a rich set of material options to enhance the quality of 3D models. I'd also like to highlight our support for point clouds. Our implementation of point cloud rendering is based on Autodesk Recap's RCS file format, a powerful format that supports levels of details and enables interaction with massive point clouds containing hundreds of millions or even billions of points. We've integrated RCS deeply into our rendering engine, allowing us to visualize large point clouds efficiently with optimized resource usage and smooth navigation. A primary goal of nearly every visualization engine is to improve the visual quality of rendering results. To achieve this, advanced features of effects are often added to the engine. However, with real-time rendering, it's essential to implement these advanced effects in a ways that won't significantly impact performance. The ODA Visualize SDK includes several such features. First is support for shadows, with an extension to ground shadows. Shadows are supported on all platforms, including mobile and WebGL with stable performance. You can see the result on screen. Another popular feature supported in Visualize SDK is reflection planes. This functionality enables realistic reflections on planar surfaces within a graphical scene. The next feature to mention is screen space ambient occlusion, a rendering technique that adds a global illumination effect to the scene in real time. Our implementation uses enhanced blur to reduce shadow noise, and screen space ambient occlusion can be adjusted for different zoom levels, either manually or automatically. In any engineering application, selection functionality is essential. Although selection isn't directly related to rendering, users expect to see it in visualization engines. The ODA Visualize SDK includes this functionality, supporting both simple click selection and window selection. Additionally, Visualize SDK includes a GPU-based selection implementation, enabling fast selection actions such as mouse hovering and as part of tools like measurement tools. Selection in Visualize SDK supports different levels, allowing selection of an entire object, individual geometry, primitives with an object, or even individual faces of a triangulated body. Selection is often paired with highlighting, as selected objects usually need to be visually distinguished. Visualize SDK offers this functionality and allows customization of highlighting styles. In addition to basic color changes, you can control the visibility of edges and faces or render highlighted objects or object parts on top of others. It's important to note that customizing highlighting styles may increase resource consumption. For example, if a scene is rendered in shaded mode, where edges or user lines aren't loaded for rendering, adding edges to the highlighting style will load them into the rendering engine, increasing load. Another notable feature provided by Visualize SDK is visual styles. Visual styles allow for impressive visual representation, even for relatively simple models. Adjusting a few visual style options such as edge mode, edge crease angle, and face transparency can significantly improve rendering effects to the final model representation. In some cases, this approach is more convenient and faster than adjusting material properties. Certainly, it's not the full list of features available in Visualize SDK. Our other features include fast transform, which allows real-time metrics application and real-time isolation or geometry pipeline. Sectioning is also worth mentioning. Visualize SDK provides GPU sectioning with a very fast but offer only a visual result of the section, and CPU sectioning, which is slower but provides the section geometry as a plain shell or polyline. Additionally, Visualize SDK includes an animation API. The SDK also offers various extensions and examples based on its API, which users can leverage. For instance, there are examples of markups and measurement implementation in our Qt-based samples, as well as sample implementation of the View, Cube, and VCS ASs. Visualize SDK also supports extensive data import capabilities from multiple formats, along with several export options. To complete this brief overview of Visualize SDK, we'd like to highlight two features that at first glance may seem unrelated to rendering, but could be valuable to users. The first is collision detection. Collision detection is a popular feature in engineering applications. For example, it allows users to check a building model for potential conflict between parts that should not intersect, such as electrical and plumbing components. Visualize SDK provides two collision detection modes. The first mode in intersection mode, where collision is detected if the penetration depth exceeds a specified value. The second mode is clearance mode, which detects all intersection and contacts and flags collisions when the distance between two objects is less than a specified value. Finally, we want to close this overview with a feature called progressive mesh. There's a special geometry primitive in the Visualize API that can be created based on the input shell object, or in other words, is a triangulated body. This object can generate its own representation at varying level of details and can dynamically switch its level of detail in real time. Now it's time to talk about our latest and ongoing development. Starting with a particularly interesting feature, text anti-aliasing. As it's well known, letters in TrueType fonts are represented as vector geometry based on splines. In the ODA Visualize SDK, triangulation has traditionally been used for rendering such fonts. This approach has certain drawbacks. Small letters can appear pixelated, and large letters may look segmented due to fixed triangulation accuracy. We experimented with different approaches to solve this issue, such as combining triangulation and textures. However, this method could cause inconsistencies when two adjusted letters are rendered differently. Now we have implemented a new approach that processes vector geometry based on splines directly on the GPU. This solution provides a smooth, clear rendering result for both large and small letters without performance issues. The next feature we'd like to highlight today is instancing. Instancing is a technique that allows us to draw multiple identical objects, different only in wall transformations, with a single render call. For several years, we considered adding this feature, but since only DWG format data included repeated objects, and this data often has differences beyond transformations, we postponed its implementation. However, once ODA began supporting the Navisworks and a large set of mechanical formats, the need for instancing became more relevant, and we implemented it last year. ODA has been steadily increasing the number of supported file formats each year. Many of these formats have a hierarchical structure within their databases, such as PRC and various mechanical formats, which are now one of primary focus of the development. Hierarchical structure often made data management easier. In the past, the visualized database structure was linear. In most cases, models contained a simple list of objects. The only exception was with blocks and insert, but that's a separate matter. This linear structure meant that after importing data into the visualized database, users couldn't interact with objects at the same logical level as in the native database. This issue was partially addressed with common data access mechanism, but CDA performance may not be optimal for certain formats and for certain cases, and some formats still lack CDA support altogether. To address this, we decided to implement a hierarchy support in the visualized database. Well, a new object called group was added to support this. A group object can contain entities, inserts, or other groups, enabling multiple levels of nesting. The group object also supports transformations, materials, and other attributes which apply to all its children unless overridden by the children's own attributes. Operating like highlighting, isolation, or animation can also be applied to the group object, simplified model manipulation. We selected PRC files as the first example for using this new group object. One reason was that our previous PRC to visualize import implementation lacked sufficient quality, as it didn't allow for importing multiple views if they were present in the PRC file. The resulting database had a flat structure with only a few entities and no hierarchy, making logical manipulation of same data difficult. Another motivation was the PRC format similarity to visualize, making it feasible to implement an accurate import that support most PRC features. This task has been successfully completed, and a new PRC to visualize import implementation is now in place. The new import supports all major PRC features, including multiple views, annotations, cutting planes, and exploded views without any duplication of geometry in the visualized database. Thanks to the group object, we could replicate the native hierarchical structure of the PRC file in the Visualize database. Next year, we plan to integrate the new group object into other import modules. The first candidate are Navisworks and a new module for importing data from GLGF. As it's well known, Revit has the ability to export data to DWG. This functionality is particularly popular for a type of Revit view called sheets, which are similar to DWG paper spaces. Consequently, Revit exports its sheets to DWG paper spaces. The ODA BMRE SDK does not have this capability, but ODA received many requests for such functionality. After some discussion, it was decided to use Visualize SDK for this task. Visualize SDK can import data from Revit into Visualize, and it also has the ability to export data from the Visualize database to DWG. Thus, Visualize can serve as an intermediary in the two-step process for exporting Revit sheets to DWG. In the first step, data is imported from Revit into Visualize, and in the second step, it's exported from Visualize to DWG. However, this task was not straightforward, as it required significant extension to the export from Visualize to DWG module. Initially, this module only supported export to model space. As mentioned, Revit sheets are similar to DWG paper spaces and contain multiple viewports, which were not supported in the original Visualize to DWG export. The second challenge was that in Revit, most geometries are represented as 3D objects, even in sheets. Therefore, during export to DWG, these must be converted to 2D objects, requiring additional functionality to handle the 2D projection for these transformations. It also was noted that in this two-step process, the final result depends on the outcome of the first step, the import from Revit into Visualize. For example, BMRE SDK does not support blocks or layers. As a result, after importing into the Visualize database, there will be no blocks or layers, and accordingly, there will also be absent in the final DWG file. Generally, this procedure can be described as import through render. The primary goal of this approach is to achieve a visual result as close as possible to Revit's native export from Revit files to DWG, although the internal structure and object types may differ. This year, we have continued working on the 2D CPU device, which is designed exclusively for CPU-based use. The motivation behind this device is that engines like DirectX or OpenGL are best suited for the 3D rendering, while they can and are used for 2D rendering, as seen in applications like AutoCAD, and it often makes sense to create specialized CPU devices for 2D drawings, as they can be comparable to and in many cases faster than traditional 3D rendering engines. The development process for this device is highly research-oriented. We are exploring various approaches and optimization techniques. For instance, we implemented a method that replaces small text on the screen with filled rectangles. Since this optimization applied for small on-screen text, it doesn't significantly affect visual representation, while improving performance. As drawing, a filling rectangle is much faster than rendering text precisely. Currently, we are actively working on another optimization. During a pen action, we replace true panning with raster image movement. We anticipate that this technique will significantly boost performance, and early results are promising. However, some technical issues remain, such as handling parts of the image that moves off or onto screen. Another future research area is optimizing zoom-in performance. Additionally, we are investigating other issues such as achieving smooth and fast rendering when tool performs action as it requires constant update to temporary geometry. Well, so I see on slide we already switched to the next feature. This year, we have continued developing ray tracing functionality as part of our focus on improving rendering quality. Ray tracing enables the visualization of photorealistic images with various real-world material effects. It's widely used in products that require final, high-quality rendering, as ray tracing techniques involve intensive calculations. Primarily, finding intersection between emitted rays and scene geometry and calculating material properties on surfaces. This process usually requires substantial rendering time. But what if we want high quality ray traced effect in real time? With modern fast GPUs, this is becoming increasingly achievable. Of course, even top-end hardware can't even deliver absolute photorealism in large scenes, but with simplified effects, emulated heavy effects, and limited calculation, impressive results are possible. ODA is working on a real-time ray tracing solution, experimenting with different approaches to achieve better and faster rendering for supported products. We are developing two ray tracing engines simultaneously, one CPU-based and one GPU-based. A purely CPU-based solution can be fully real-time, but we introduce and debug experimental features there, first optimizing them before porting to the GPU-based engine. CPU-based ray tracing can run on any platform and produce images with shaded geometry, which can be useful for certain expert and server-based applications. However, our primary goal is a GPU-based real-time ray tracer, and we are progressing in this direction. Currently, we are working on solutions that can run on a majority of GPUs, supporting at least OpenGL4. Using GPU ray tracing, we automatically achieve several effects inherent to ray tracing, including clear shadows, unrestricted by shadow map resolution, natural light path through semi-transparent surfaces, refraction on glass materials, and realistic reflection on smooth surfaces, independent of the complexity or quantity of reflective geometry. Rendering each frame requires emitting thousands of rays, for which intersections of the scene geometry must be found. To improve rendering performance, we apply geometry preprocessing and sorting to create an effective bounding volume hierarchy. This hierarchical structure optimizes the ray intersection process. We are also exploring the possibility of adding more complex effects, such as surface roughness, global illumination, and ambient occlusion. These effects would require additional rays and specific process optimizations. Using the OpenGL API to work with the GPU offers many advantages. GPU ray tracing can operate within the same environment as the generic OpenGL render, utilizing the same textures, geometry buffers, and other resources. This setup potential allows us to reduce GPU load by using the generic renderer where possible and applying ray traced effects only where needed. For example, adding realistic reflections or ray traced shadows selectively. As ray tracing usage grows, real-time rendering continues to become more realistic. For instance, NVIDIA's latest products includes RTS technology with dedicated computational units designed specifically for ray tracing. In the future, most GPUs will likely support ray tracing solutions, and we plan to support these advances. For now, however, our primary focus remains on optimizing performance for standard hardware. Development of real-time ray tracing is actively ongoing, with the first stable version expected next year. Over the past year, we have put significant efforts into improving support for large files. One of the outcomes of this work is a new assembly mechanism. So, what is an assembly? Imagine you have a set of different files and want to visualize them all in the same scene. We call this combined scene an assembly. Previously, Visualize SDK provided two methods for creating such assembly. The first method used the TV database append function, which reads an original file, converts its contents to the Visualize format, and stores it in the existing Visualize database. The second method separated data conversion from assembly creation. In the first step, input files were converted to VCFX files, and in the second step, you manually copied the VCF file content into the assembly database. Both methods involved copying data, either during conversion or through direct VSFX copy, making assembly creation a time-consuming process. Additionally, the resulting assembly typically stored all combined data at runtime, which could require substantial memory. Now, Visualize SDK includes a new assembly mechanism, model reference, that improves on the second approach. Instead of copying VCFX file content, you can create a model reference object that points to the model in the input VCFX file. In this case, no data copying occurs, so the process is fast and does not require additional memory. This allows you to create and recreate assemblies from a large number of files efficiently. If the input VCFX file supports partial viewing mode, model reference will also support it without additional configuration. A single Visualize database can combine both models and model references in the same scene. So model reference does not impose any restriction on other database content. We are also continuing to improve the partial viewing mechanism, which is designed to visualize large files that cannot be fully rendered. This year, we added an alternative filtering mechanism, more suited to 3D cases, and similar to the Beam&V SDK's filtering mechanism. Various updates to partial viewing notifications introduced last year enhance application interaction. Now, partial viewing can notify the application about the number of processed objects, allowing new data vectorization to be divided into smaller groups and helping to prevent application freezing. We also added an object ignoring criteria, which means that if an object's visual extents measured in pixels are smaller than a specified value, this object will not be loaded during the partial viewing process. This optimization speeds up the process and reduces memory usage, as partial viewing ignores objects within the visualized extents that are effectively invisible. Our current implementation of partial viewing has two main issues. The first is the potential for application freezing during the vectorization process. As vectorization is currently a single-threaded operation, the second issue is high memory consumption. Typically, a visualization process based on VCFX file involves two steps. First, loading objects into operating memory to create a high-level representation of the objects stored in the Visualize database. And second, a vectorization step, which generates a low-level representation of the objects stored in the GS cache. This means we store two types of objects in RAM, Visualize object and GS cache. To address these issues, we are developing a GS cache storing mechanism. The concept is to replace the original geometry primitives in the VCFX file with the generated GS cache and a simply stub containing basic information. When this file is loaded, only the stubs are loaded instead of the original visualized objects, which reduces memory usage. Additionally, instead of performing vectorization, the saved JS cache is transferred directly to the JS system, which boosts vectorization performance and at least partially resolves the freezing issues. The JS cache storage mechanism is still under development, but even at this stage, we are already seeing a reduced memory usage and improved vectorization performance. It's important to know that this feature is primarily useful for viewer type applications, and these typically don't require extensive editing capabilities. Some actions like markups are possible, but not much beyond that. So that's it about our Visualize SDK for today, and now we are ready to move to the QA session, and we are ready to answer your question. So to have the communication with our team, and so you can see that maybe I'll introduce some guys. It's Alexander Fedorov. It's our team lead, team lead of our Visualize team, and our senior developers. I see Andrei Markovich here, Yegor Slupko is here, Vlad, Vlad Malka is here. I see, he's online. I see Kenny Nikolaenko, here. Yeah, it's nice. Anton Terletsky is here. So yeah, we are ready to. Alexei Zakharov. Okay. I would like to. So, Alex, you can continue with answering the question and.
Okay, thank you, Sergey, for the presentation. And yes, we already saw a few questions. So the first question was, will the mentioned extras also be released in ODA SDK, and if yes, when? Especially the highlighting would be interesting for us. So yes, all features which was mentioned in the extras block of our presentation are already implemented and released. So you can freely use them. The next question was about supporting of the hierarchy structure for partial visualization. Yes, our partial viewing mechanism already supports a new hierarchical structure of our database. The next question was about support of the MEP load calculation module also. So here the situation is the following. If this calculation module was from ODA SDK, so yes, it is supported. But if it was mentioned some third-party model, so then it can be included in the list of supported formats only. The next question was about implementation of the view kube, or example of the view kube inside our MFC samples, and also about the ability to activate it and to translate the text on its sides. So currently no, implementation certainly can be used in ODA MFC app because it's some part of extension over our base API. But example of using is currently present only in our Qt-based application. But certainly, if it will be strong interest, we can add also support such view kube to our MFC sample. Because the idea of our MFC sample was that it should be quite simple example just for start of using our SDK. And we don't want, at least on the first stage, don't want to put there too much functionality, because in other case it will be not very good for the first start. Yes, and also when I speak about our Qt samples, I mean not only our audio viewer, our multi-format viewer, but also our other format-specified viewers like OpenAFC viewer and OpenStep viewer. In all those viewers, view kube functionality is included, and it can be including ability to translate the text, and can be investigated how it works.
No, I mean
so
that,
that's all for now.
Yeah,
about
yeah. I mean that it's all question in the list that I see. Yeah. Oh, okay. It's okay.
Also, I saw some question about iOS support. Yes, Visualize SDK works on iOS mobile platform, and we also have sample iOS sample which demonstrates how it works.
Yeah, we are following. So I don't see question.
I also should mention that we also have samples for Android platform for VPF case. Certainly, samples have a little bit different functionality. So our most powerful examples are for the desktop and Qt-based. But also, for example, sample for the VPF also have quite significant amount of functionality and can be used as example of how to use our Visualize SDK with Swig wrappers for the in .NET applications.
Yeah, I see one more question.
Yes, I see the next question about Visualize. Is Visualize used with drawing API? So Visualize has extensions which allow us to import data from the drawings from the DWG file. So certainly this module interacts with public API of Drawings SDK to perform this functionality. And here I also want to mention that we have two levels, two kinds of API of our Visualize. So we have high-level API, which we call TV API, which is a very common interface, allows us to manipulate directly with simplified API, which allows us to manipulate with geometry and all other attributes of the drawing scene. And also we have so-called low-level GI.js API. This API are usually used inside many of our other projects. So, for example, DWG also use this low-level API for its drawing, and BMRV, Navisworks, practically all of our SDK uses low-level API to visualize their data. And our simplified API, TV API, is just a simplified, convenient wrapper over this functionality. So the base functionality is the same. And if you are working through the drawing API, you also have ability to use the same set of features that we have discussed now in the context of our high-level API. Maybe not so fast because we have some simplifications, have some additional extensions, but all functionality which implemented in high-level Visualize API are possible to be achievable through Drawings API, through BMRV API, and so on.
Yeah, I also wanted to add that not only Drawings API, but any API, any format API that we have. Yeah.
Yes, I saw the question about the case that iOS sample doesn't compile out of box, so we will check it, and certainly if something is wrong, we will fix. The next question about Visualize JS for web and ability to find API document about assemblies. So as we talked today, assemblies are currently under development, and now we are working on the last stage, ability to stream this data, and this is the main part of functionality which is need to use it in the web. So as soon as we will finish this functionality, we will include it to the we will wrap it by Visualize.js and give access to our web platform. And after that, I think we will add the documentation about assemblies. The next question about support of newer version of DirectX. It's a very good question because we, during a few last years, we have such task in our long perspective list. But such work is really quite time consuming, and I suppose we need to have additional number of requests to initiate this work, because certainly we think about it, because it also will be quite convenient for the VPF applications where DirectX is a native rendering engine. But currently I can say that we will plan to implement this next year, but we remember about it, and again, if we will have enough requests, I think we will be able to speed up the start of such work.
No, yeah, I think we wait for a couple of seconds for maybe we have more questions. I will just.
And also, I would want to add that if you will still have some questions, next week we will have individual meetings, so all of us are free to set up some time, and we can discuss any problems, any questions in more details next week, from 26th of November till 28th of November.
Yeah, and not only problems and issue in our code, but if you have some issues how to use our code, you can use this opportunity to ask us question or get some guide personally during the meetings. Oh yeah, we have one more, but it's
yes. I see the next question about about Visualize.js. Here I should mention that Visualize.js is and the Web SDK is more close to our web team, but I try to explain at least what I know. So as I know, today we have discussed two kind of ways how it is possible to create assemblies before our new idea with model reference. The first one was just using append mechanism, and here we should mention that append works, for example, with few files other than VSFX. So, for example, you have one IFC file, second IFC file, third IFC file, and using appending functionality, you can combine it all together in one visualized database. The second way, which was discussed and called copy, is possible in theory, but currently it is not used, at least as I know. And as I know, our Web SDK colleagues also use the first way when they append different files of some specified formats. And our new mechanism with model referencing, as I already mentioned, I believe that it will be ready at the end of this year, maybe at the early beginning of the next year, when we will finish streaming. In this case, it will be open for use in our Web SDK solution. Yes, maybe I was small mistake because I don't see that you in the last question you have mentioned that not about the VSFX files, you have mentioned VSF files. So here I want to mention that VSF files is our old format, is certainly still supported, but I think it will be much more, it will be the good decision to move to the VSFX file because it's always currently under development. We add some improvements to this format and so on and so on. So VSF files, I'm not sure that even it supports partial viewing without certainly additional conversion to the VSFX file. So VSFX file is now our primary format for the Visualize database, I mean, and it will be the good strategy to move from VSF to VSFX files.
In general, a good strategy to move to new releases and new functionality to get new features, improvements that we have. Well, I see no more questions, and I'd like to say thank you for everyone for participation. Thank you for using our toolkit. We are always welcome to get your feedback, to get your questions. We are happy to answer to them. And from my side, I would like to say thank you to our team. Not only for participating in this meeting, but also for and mostly for the development of our nice toolkit, and we are trying to do the best for our members. So yeah, thank you all.
Thank you all. Thank you for your attention, and we are waiting you to individual meetings.
See you.